All right, so now we're going to look at how we perform two-sided tests. And the lucky thing is that they're pretty much the same deal as one-sided tests. All you really have to do is know when you're dealing with them, and the math is really just multiplying your p-value by 2. But let's look at an example so that you can really understand how this works. Okay, so we use two-sided tests when our alternative hypothesis claims that the proportion is not equal to the null hypothesis proportion, like whatever that is. So we're basically saying not equal to. So it's not saying that it's greater than, and it's not saying that the true proportion is less than. It's saying the true proportion is not equal to what the null hypothesis is claiming. So when you say it's not equal to, it could be, greater than or less than. That's why I say two-sided, because we have two sides that we got to look at the p-value for. So it could be, going to the right or going to the left if you're looking at a graph. So let's look at this example. So here we got the accounting firm AJ&L and Associates. They audit a company and they look into their financial records for fraud. And this is actually true if you're wondering. They use something that's called Benford's law. This is basically a law that states that the distribution of first digits in many real-life sources of data is not uniform, meaning that like even though how we use 10 digits for our number system, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, the chance of the first digit being 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0 is actually not 1 in 10. It's actually not 10% for each of them. Most people would think that it's actually, follows a different distribution. And here it says that it's actually that 30.1% of them will begin with the digit 1. So they should expect that 30.1% of the numbers in the financial records should begin with the digit 1 if there is no fraud. So this is actually true, and some people don't know this. So when they're checking to see if you're making up your numbers and if you're making up data, trying to maybe cheat taxes or something, they check to see if you have a suspiciously large difference of your digits not beginning with 1 from 30%. So maybe you only have 10% or like 50% or something, So if they find, that the proportion is significantly different from this proportion of 0.301, then they're going to do a much more thorough investigation. So they're probably going to audit them, in other words. So what they do is they took a random sample of 300 expenses, and they found that only 68 of them began with the digit 1. Based on this, should they do a more thorough investigation? So this is a case of a two-sided test because it could be that the proportion is far less than 30%. Maybe the proportion is 5% or 10%, or maybe it's 60%. So either direction would be evidence for fraud. So this is a two-sided test because you have to take both ends of the, the tail ends into account. So let's go ahead and let's work through this using the 4-step process again. Our statement, null hypothesis would be that the true proportion P is 0.301. Alternative is that it's not 0.301 and doesn't specify an alpha level. So we're just going to use 0.05 as the alpha level. And remember to define what P is. P represents the true proportion of all expenses that begin with the digit 1 at this company. All right, now we go to our plan. If the conditions are met, remember, we're going to use a one-sample z-test for P. So again, we check the random condition. It says in the problem that a random sample was used, so that's met. 10%. If this is a large company, is 300 no more than 10% of the total number of financial records? So is there at least 3,000 in the population? And yeah, it's a big company. So there's probably gonna be way more than 3,000 financial records for this. And then the large counts. Remember, N P naught. We assume the population proportion is 0.301. So we do the 300 times the 0.301 and 300 times 1 minus 0.301. We get 90, or very close to 90 essentially. And then that means 210 will be the other one, because remember, this plus the failures, they both have to add up to 300. So both these are at least 10, so the conditions are all met. Now we go to the do part, which is the fun part. It's just the math calculation. So we just got to use our formula. Remember, for our Z statistic, or Z score, or whatever, Z test statistic. So remember, let's flip back to it actually, so we can see refresh our memory. So here we had that 68 of them out of 300 began with 1. So our P hat is going to be 68 out of 300. And our P naught again is a 0.301. Our N is 300. So we work it out, as long as you don't mess up with your algebra. You should get roughly about negative 2.8. Negative 2.8-ish. Now, then we start off as usual. We look for like the probability of getting a proportion less than or equal to or less than this. So let me actually do a little side note here. We don't just jump to that. Let me cover that for now. So remember, our p-value is going to correspond to the area to the left of this. So negative 2.79. This is going to be our p-value here. And remember, this is standardized, so this is a normal distribution with a mean of 0, standard deviation of 1. So we find this p-value, and then we multiply it by 2, because we're looking also at this p-value. We're adding these two together. So using technology, so I'm going to go through a little faster this time, because I assume you're proficient. Go to normal CDF. The lower bound could be negative a billion or whatever, comma, negative 2.79 as the upper bound. Mean 0, standard deviation 1. This will give me the area to the left. It'll give me that area over here. Then we just double this, and that'll give me both areas. So we get 0.005. So we get something less than 1%, as you can see there. We get a p-value of less than 1%. Let me write that, make that a little more clear looking. P-value of way less, well, not way less, half a percent, but our alpha is only 5. Alpha is 5%. So think for a second. What do we say? Do we reject HO, or do we fail to reject HO based on that? Think. So since our p-value is less than our alpha of 0.05, we are going to reject HO because we have convincing evidence that the null hypothesis is not true, and that the true proportion of all expenses that start with the digit 1 is actually not equal to 30%. So since it's not equal to 30%, we probably would advise them to do a more thorough investigation of this company. They might be, committing fraud, and looks like they might be getting caught too, unfortunately. All right, so now we're going to follow this up with a confidence interval, because it's going to be really cool for you to see and understand how confidence intervals are connected with significance tests. So referring back to that same problem, we're going to find and interpret a 95%, wrong side of the bookmark. We're going to find and interpret a 95% confidence interval for the proportion of all expenses that begin with the digit 1. Now, remember, confidence intervals are a little different in the sense you're actually trying to figure out what the true proportion is, where the significance test is you're just seeing if the claim is, is reasonable. We're trying to see if it could be true or not. Like we want to see, like, is it reasonable enough to say, yeah, this could be true, or is it like too extreme for us to be like, yeah, this is not true. But again, remember confidence intervals, use the 4-step process. Start with our state. We would like to estimate P, true proportion of all expenses that begin with the digit 1 at a 95% confidence level. So remember, still define the parameter and the confidence level, all in context. Our plan. We want to construct a 1 sample Z interval if the conditions are met. So we check the same conditions, but one part is a little different, so I'll show you. Random samples, again, use, we can say it's met, 10%. Again, same thing. We can just basically say that it's reasonable to assume that there's at least 3,000 expenses in this company's financial records. So this is met. All right, large counts. Now remember, this doesn't have a null hypothesis for the large counts. There is no null hypothesis. Like there is no null hypothesis proportions. There's no P naught. So remember this, we use the P hat. We check to see if N P hat and N times 1 minus P hat is at least 10. So these values are going to be a little different. So don't confuse that, because that's a common mistake when students go back and forth between these two types of inference methods. And let me just pop back to show you what I mean. Remember it was N times P naught, and P naught was 0.301. Here's N times P hat, because remember, we don't have a P naught for confidence intervals. In either case, it's still at least 10, so all the conditions are met. So now we can construct our confidence interval. And let's not forget our form. I know it's been a chapter or so, but I don't want to give it away already. But remember, our point estimate, P hat, plus or minus our critical value, C star, times the standard deviation of the statistic. And again, use P hat, not P naught for this, because we don't have a P naught when we're making confidence intervals. So we get this. And remember where the Z star comes from? That's going to be the critical value, or the Z value, that corresponds to 95% confidence interval. That's not a good, let me try again. And we have 95% in the middle. So this is our positive Z star, and this is our negative Z star. So what would the Z star values be that correspond to the right and left endpoints of the 95% area that's enclosed? Remember, again, normal distribution, mean of 0, standard deviation of 1. And it's used so much as you should know, about 1.96. P hat, remember the 68 over 300. Going through that, make sure you don't mess up on your calculation. You'd get about 0.227 plus or minus about 0.047. So you get your confidence interval to be about 0.18 to 0.274. All right. Then we conclude, a little different, but just always be thinking when you're working on this stuff, because you don't want to make a like a brain fart mistake. You don't want to, or silly mistake, I'll say. So our conclusion is that we're 95% confident that the true proportion P lies in here, is anywhere from 0.18 to 0.274. So remember, that's pretty simple because that's what we get. We're 95% confident. That's what we got. That's our interval. That's our range of value, so to speak. And well, we're going to follow up with the next question in just a second. So just again, make sure you always interpret your conclusion in context. 95% confident that this interval captures the true proportion of all expenses at this company that begins with digit 1. So it could be anywhere from 18% to 27.4%, but not really, not literally, because it could be anything. Remember, this is just 95% confidence interval. Now, the follow-up question, which I almost gave away, but here it is again. Does your interval that we just got, part A, does it lead to the same conclusion as the significance test? So let's go flashback to the significance test. The significance test told us to reject the null hypothesis. It said that we think the null hypothesis is not true. We think it's a lie. We don't think that the true proportion is 0.301. So we don't think it's 0.301 based on that. Does this lead to the same thing? And again, just think logically. Well, of course it does. Why? Because this doesn't have 0.301 in the interval. So if it doesn't have 0.301 in the interval, it's basically saying that it doesn't consider it to be a plausible value. Now, remember, we say plausible not to mean possible. We just say plausible to mean reasonable, like a reasonable guess, or reasonable, guess based on our statistical analysis. So they both, lead to the same conclusion. So again, this, reinforces our decision to say, yeah, you guys should probably investigate these guys for fraud. Unfortunately, it looks like they're up to something shady. So yeah, they're both good. And then, yeah, it's once you start seeing this, it's really cool to really now actually recognize how this stuff could work in real life, because it's used all the time. All right, so I hope that helps. Good luck.